In part 6 of the introduction to standardized echography, we will explain another acoustic phenomenon of large interfaces, the refraction of the ultrasonic beam, and B-scan artifacts caused by refraction. Extremely large interfaces may cause refraction when they separate media with different sound velocities. Refraction occurs toward the perpendicular when the beam enters from a faster into a slower medium when crossing the interface. Like in reflection, all the beams, the incident, reflected and continuous beam or refracted beam, are lying in the same plane. The reflection angle is equal to the angle of incidence, but the angle of refraction, beta, is smaller than the angle of incidence when the refraction occurs toward the perpendicular. Here too, the angle of refraction is the angle between the ongoing beam and the perpendicular to the interface. And then there is a refraction away from the perpendicular. That is when the beam comes from a slower medium entering a faster medium after crossing the interface. In this case, the angle of refraction, beta, is larger than the angle of incidence. When refraction occurs away from the perpendicular and the incident beam gets larger than a certain amount, a special situation may arise. The angle of refraction may get larger than 90 degrees and all the energy is totally reflected, cannot enter the next medium, where we have an absolute acoustic shadow. There are basically three causes of acoustic shadowing, ranging from light to absolute density. High reflectivity is one. High reflectivity at air and gas surfaces. Absorption is a frequent one. The normal lens or bone, calcium deposits, dense blood, silicone oil, they all absorb much energy and can cause acoustic shadowing. And then total reflection that we have just mentioned, with the refraction angle getting 90 degrees or larger, so at oblique sound entrance into a faster medium. These are the three causes of acoustic shadowing that we're dealing with in echography. Refraction away from the perpendicular is often a nuisance. It causes artifacts and that may lead to misdiagnosis. How do we avoid it? In A-scan easy, beam perpendicularity that is required for large acoustic interfaces in standardized A-scan avoids refraction entirely. In B-scan, we can center the investigated area that caused the artifact with an oblique beam. We can center it in the B-scan and avoid the obliqueness of the incoming beam. At least these artifacts should be recognized, and this way misdiagnosis should be avoided. Again, in standardized A-scan, refraction artifacts are eliminated automatically by the perpendicular beam, which is a must for evaluation of large interfaces anyway. In B-scan, artifacts always occur. Here, for instance, a retinal detachment. When we look at several areas of these retinal signals, they're holes. These are not defects in the retina. These are shadows, total shadows caused by total refraction of the oncoming oblique beam. And there is another artifact right here. It appears that this choroid is detaching peripherally more and more. A similar artifact is seen in the episcleral space. This is the occasion where we will center this area in the beam and the artifact disappears. Here are other B-scan artifacts caused by oblique sound beams, with showing here a marked thickening of the detached choroid. And here again these holes, which are artifacts, they are caused by the retina, which on the surface of the detached choroid is slightly folded and causes this total refraction at certain points of the oncoming oblique beam. Also, an artifact of different kind, we see here long lines. They come from one point of the retina hit by the beam perpendicularly. But since the beam is wide in that area, this signal is shown as a line rather than a point. Orbital pseudolymphoma of the lacrimal gland. When we look at this B-scan, there are defects here and here. And these defects are enhanced when we decrease our system sensitivity to get better resolution. It's a consequence of total reflection at the obliquely hit anterior surface of the capsule of this tumor. This young man had a large cyst, episcleral cyst anteriorly. We see here B-scan that suggests a communication of the cyst with the vitreous cavity. That's an artifact caused by total reflection at the surface of the eyeball and the cyst wall. And the way to recognize and avoid this is by just shifting the acoustic section and be perpendicular on these walls of the cyst and of the eye. In A-scan we don't have this to begin with. That is the cyst wall hit by a perpendicular beam, and when we decrease our system sensitivity, we see here the two peaks from the inner and outer surface of the cyst wall. In immersion B-scan, artifacts are much more frequent. Here the historically famous Baum's bumps. Baum introduced B-scan into ophthalmology, and he used only immersion B-scan, and these artifacts caused by the anterior surface of the eye on the lens are called therefore Baum's bumps. Here we see a tumor of the iris. Refraction toward the perpendicular. This is the good guy. It can be very useful and may even be necessary for our diagnostic purposes. Namely, the optic nerve structures and extraocular muscles can be measured even back in the orbital apex only because of refraction of the oncoming sound beam towards the perpendicular. For precise measurements of the optic nerve, this refraction towards the perpendicular takes place at the outer layers of the dura. The more oblique the incoming sound beam, the stronger is this refraction towards the perpendicular. And this refraction takes place until the sound beam arrives in an almost perpendicular fashion at deeper layers of the dura. This allows measurements of actual optic nerve sheath diameters, that is the arachnoidal and pial diameters, going back into the posterior orbit even. And this is not a mistake. It happens. This is the refraction at the outer layers of the dura. The more oblique the sound beam comes in, the more refraction occurs until the beam is almost perpendicular in deeper layers. If we want to measure the thickness of the dura, we cannot measure this on this side, because until the beam is refracted to the perpendicular, we have lost outer layers of the dura. Always measure the dural thickness, therefore, at the opposite side, where the beam already arrives perpendicularly. And this is the way these surfaces are recognized and measured. We have here the highest spikes from the arachnoidal surfaces, and their distance gives us the arachnoidal diameter. Of course, they have to be maximized. These are the dural surfaces, and when you look carefully, you can already recognize that this dura here is not as thick as here, for the reasons we just mentioned. And the pial diameter. The dural thickness, therefore, should be measured on this side, opposite the incoming beam. Refraction toward the perpendicular for precise measurement of extraocular muscles. It occurs similarly. It takes place at the outer layers of the muscle sheaths. The more oblique the incoming sound beam, the stronger is the refraction toward the perpendicular. And the refraction takes place until the sound beam arrives in an almost perpendicular fashion at deeper layers of the muscle sheaths. This allows measurements of actual muscle sheath diameters anywhere in the orbit, even within the orbital apex. So this is the good guide, the refraction toward the perpendicular. And here an example. The probe is placed opposite this medial rectus muscle and the beam is aimed perpendicular at the sclera, and the area where we have here the number 3 measuring zone, because there is no optic nerve here that can interfere. Reliable measurements are only in straight gaze available. So we start with measuring point 3 and then angle forward to measuring point 2, to measuring point 1, or for measuring point 3 posteriorly to measuring point 4 and measuring point 5. So measuring point 3 is always first, for the reason I already mentioned. The optic nerve doesn't interfere here. The muscle lies right next to the bone, and as for angle the beam a little bit more posteriorly, anteriorly that is, the muscle goes away from the bony surface. So we aim as far posteriorly as we can to get a maximum signal of this muscle surface next to the bone surface that is still close to 100% display height. That's the way